Welcome to Empowered Learning. This is the first video in the video series on the review of sequences for its use in calculus. So in this video series, we're going to talk about what a sequence is, figure out why do we need to know what the concept of a sequence is in calculus. We are also going to remind ourselves, and for some of you, expose you to several different types of sequences. And so we'll run through those. We will also talk about a series of basic facts. You can call those theorems, but we're going to run over some basic facts that come out as a result of dealing with sequences in terms of limits. And so the main idea here is that we're trying to set up the stage so that we can actually use sequences as a way to eventually re-represent certain functions that we'll have to integrate. And so the reason why this is important is because of the fact that there are some functions that if we try to integrate them, they don't have what we call elementary function antiderivatives. And so that's, to make it real simple, if you are studying, let's say, a calculus 2 or calculus B, at your particular institution, or just you're reviewing it on your own, you've probably gone through a bunch of integration techniques. So you've probably reviewed things like U substitution, integration by parts, trig substitution, trig integrals, partial fraction expansion, so on and so forth. Okay. So whenever we cannot evaluate an integral by any of those means that I just said, then more than likely what it turns out being is that we either have to use numerical method techniques to do integration, like Riemann sums, trapezoid rule, Simpson's rule, to be able to do that. Or what we want to do is essentially re-represent our function as a polynomial. And so in the process of doing that, the first thing that we will have to do is be able to recognize the particular sequence that that particular function would produce. Okay. And so we're kind of doing this parallel thing to what the actual function is as a continuous function, meaning that we're considering all the x values in this domain, and we're going to sort of compare that to what its corresponding sequence function will look like. It'll look similar to it, but the domain will just be limited by just the natural numbers that we use. And so again, the idea is that we want to sort of rewrite or reframe what that function looks like, because if we can rewrite that continuous function to sort of simulate a polynomial, then we all know how to take the antiderivative of polynomials. We just use the power rule for antiderivatives for polynomials, and it gets relatively simple. Okay, and so that is the main idea here. Of course, I'll be making other videos that will eventually lead up to things like Maclaurin series, Taylor series, binomial series, where we actually take our function and actually forming it into some polynomial, and we'll have to find out for what values of x with this polynomial that we're going to use to be able to mimic what that function acts like over certain intervals. Okay, but that's far from now. Of course, this video is kind of getting into the basics, but I did want to spend some time to try to help you understand why we need to know this in a calculus course, so that you kind of know what the end of the story is before you start, so you can kind of put it in the right context in your mind as you learn this stuff. Welcome to Empowered Learning. This is the first video in the video series on sequences and how we use this concept in calculus courses. This particular video series will be split up into 3 separate videos. The first video, we will go over what a sequence is, and we'll review several types of sequences that we need to be familiar with. In the second video, what we are going to do is we're going to go over some basic facts about sequences. And so the main idea here is to get learn some of the basic properties of a sequence. Mainly, we want to know its convergence versus divergence properties, and I'll define what that is and why that's important in that particular video. But we want to look at all those basic facts and establish some definitions so that eventually we'll be able to do 2 main things. And that is, number 1, be able to form a sequence from a list of numbers. And number 2, be able to determine whether a sequence will converge or not. Okay. And so in that third video, we're actually going to go over several examples of either putting together sequences from a list of numbers or taking a sequence that's already expressed in its algebraic form and determining whether that particular sequence will converge upon some number or not. And so that's really the main aim of this particular series. So let's go ahead and get started here. So we start off by recalling that a sequence is defined simply as a function whose domain, or as you may want to think about it, its x values, is a set of positive integers. We also call those the natural numbers. To be a bit more precise or clear, we will use the following definition for a sequence. And so a sequence is a function whose domain is the subset of the set of natural numbers. And so part of the reason why I say subset is because the natural numbers are just the numbers 1, 2, 3, 4, 5, 6. But the thing is that sometimes we have sequences where, let's say, it starts off at, n equals 3. Okay, kind of like this example that I'm showing you here. Now I'll go ahead and underline it, like this example here. Since this sequence is a sequence of numbers that kind of follow the pattern of square root of n minus 3, it only makes sense for me to plug in values of n, or natural numbers n, that are 3 and higher. Because of course, if I plug in anything below 3 that is a natural number, I'm going to get a value that is not going to be a real number. Okay. And so because of that, it's proper for us to say that the domain will be a subset. Okay. Now for a sequence whose lowest number that's in its domain is 1, which is the lowest natural number, notice that that is proper because any set is a subset of itself. And so that's one of the basic things that we know about set theory, is that any set is a subset of itself. So by me saying that the function whose domain is a subset of the set of natural numbers, even the function whose domain is all the natural numbers, is still proper to call it a subset, because any set is a function of itself. So I hope that makes sense. And so it's for that reason that I make this statement here, that therefore the last definition that I just stated gives us more flexibility to express sequences where the domain of the sequences does not include all the natural numbers. Okay. So now, why do we need to know about sequences in the first place? So we recall here that integrals such as, if we want to take the most general antiderivative of e raised to the x squared dx, we can't evaluate this particular integral by current integration techniques that you've probably studied so far, because the antiderivative of this function e raised to the x is not what we call an elementary function. Okay. Basically, we can't form it. We cannot form what the antiderivative of this function is. We can't form it into a linear combination or just a combination of functions that we're already used to dealing with, like your polynomials, polynomials within the real numbers. Let me add, let's say radical functions, rational functions, logarithmic functions, exponential functions, absolute value functions, all that stuff. So there's no way for us to be able to express what the antiderivative of a function like e raised to the x squared is in any shape, form, or combination of those functions that we're used to dealing with. Okay. Now, in short, one of the most useful applications of sequences is to use them to help us express a portion of, and I say a portion of because sometimes these results doesn't always line up with what the actual function is for all values in the domain that we're considering. So, but anyway, so in short, one of the most useful applications of sequences is to use them to help us express a portion of non-elementary functions such as the antiderivatives of the following integrals. Okay. So in other words, these functions, e to the x divided by x, sine of x squared, cosine of e to the x, square root of x cubed plus 1, so on and so forth. All of these functions, if we tried to find the antiderivative of them by using the techniques taught in a first year, second year calculus course, you would not be able to find what the most general antiderivative would be. Now, if we were to put some limits of integration on each of these, we could actually find what that value is, but we would have to use numerical method techniques to be able to do it. So for those of you that have been exposed to estimating the area under the curve by Riemann sums, or using the trapezoid rule, or the Simpson's rule, that would be helpful there. But if I just wanted to find out what the antiderivative of each of these functions were, even the Simpson's rule and trapezoid rule and Riemann sum would not help me in being able to do that. Okay, and so therein lies a problem for us that we need to solve. And the first step in being able to solve that problem is to be able to say, all right, well, let's see how sequences will allow us to eventually get to a point to where we can take functions like this and find its antiderivative in terms of some functions that we know. And now, of course, we know it's not possible from an exact standpoint, but what we're looking for is another representation that will allow us to be able to do it approximately. Okay, and so I'll go ahead and kind of let the cat out of the bag here. Our goal is to eventually use sequences so that we could rewrite these functions that you see here, like e to the x divided by x, or square root of x cubed plus 1. We want to rewrite those things in terms of polynomials. And of course, these polynomials will either match up to what those actual functions that we're trying to find the antiderivative of exactly, or they will for a certain number of x values. Okay. And so what we have to do is work on what's necessary for us to be able to eventually get these functions looking in its, and I'll say at best, approximated polynomial form. The reason why we want to try to rewrite them in terms of polynomials is because in mathematics, the polynomial is kind of thought as the free-form function. Okay, I like to call it the Plato function because with Plato, you could lay Plato on anything and it'll take on the shape of that thing. And so polynomials are kind of the same way, since they're free-forming functions. Any other function that we have, whether it's natural log of x, e to the x, absolute value of x. We could express all those functions as some type of polynomial function, okay? And so if we could express these functions that you're seeing here that are integrands as a polynomial function, then you could easily take the antiderivative of it, because at this point, if you're watching this video, you probably already know how to take the antiderivative of a polynomial function. So for example, we know that x squared is a polynomial function. So if we took the antiderivative of that, we all know that that's just x cubed divided by 3, because we add 1 to the 2 here and then divide by whatever this new exponent is, okay? And of course, there's a plus c at the end. So because we're able to do that, it's attractive for us to be able to somehow rewrite a function like this in a polynomial-like form, so that we can actually take whatever result we get and do simple stuff like this to be able to get the antiderivative. So that is the main idea, okay? All right, so to summarize, the main takeaway from this conversation so far is that if we are able to express the integrand, that's say the function inside our integral, as an elementary function over a certain interval of x values, at the very least, then we can find the antiderivative of such functions with a certain range of accuracy, okay? So my discussion that I just kind of went over, that is the main point that I was trying to get across. All right, so now let's get into the actual types of sequences that we'll deal with, okay? So there are many types of sequences, but in general, the most sequences can be described as either recursive sequences or general sequences, okay? And so a recursive sequence is sequences where one or more first terms are predefined and the remaining terms are based upon those previous terms, okay? So in other words, we have, let's say 1, 2, or 3 terms that we just say, hey, we're going to start off with these. These will be the first numbers in that sequence. And remember, a sequence, again, for all practical purposes, is just a list of numbers. And we keep track of what number it is in the sequence by natural numbers. So for instance, if I have the sequence 2, 5, 8, 10, so this would be the first number in the sequence. So we say that's n equals 1. This is the second number in the sequence. So we say n equals 2. Third number in the sequence, n is equal to 3. Fourth number in the sequence, n is equal to 4. So on and so forth, okay? So in a recursive sequence, let's say that these two numbers are the ones that are defined first. And then afterwards, let's say somehow, some way we were able to use these two numbers to come up with this number here. And then for this number, we would use the combination of, let's say, what we had with these two numbers to be able to get that, okay? So that's essentially what a recursive sequence is. A general sequence is just a list of numbers. There's nothing really predefined. So if we were able to express our sequence as some function, then we would just be able to express it as a function, and that would be it, okay? Whereas a recursive sequence, a lot of times what we would have to do is have those predefined terms, and then afterwards, let's say for these last two numbers here, we would have a function representation of those numbers, but of course, it'll still be based upon what these two were to begin with, okay? All right, so let's go a little bit deeper here. So recursive sequences, let's get a little deeper into that. So many of the popular sequences that are well known are recursive sequences. These types of sequences are also known as recurrence relations. So if you read or hear the phrase recurrence relations, just know that that's the same thing as a recursive sequence. And so these types of sequences are also called recurrence relations because the predefined first terms tend to reoccur in the subsequent terms of the sequence. Okay, and so I give some examples here. So probably the most popular type of sequence that we use in calculus is the geometric sequence. And by definition, it is a recursive sequence. And so part of the reason for that is if you look at this, the first term in any geometric sequence is going to be this A. And of course, the one thing that we know about a geometric sequence is that in that list of numbers, the quotient of the number divided by the number that preceded it is always going to be the same. Okay. And so that's what this is saying here. And because of this property, we also know that whatever current number we have, we got from a previous number times whatever that common ratio is. Okay. And so with geometric sequences, we have what is called a common ratio, and that is what this R represents. Okay. So for this example that I'm showing you here, we have a sequence of numbers that can be formed. And of course, you see what that list of numbers looks like. And the one thing that's in common with all these numbers is that if I was to take, for instance, 16 divided by 9 and divided by 4 over 3, I'm going to get 4 over 3. If I took 64 over 27, divided it by 16 divided by 9, I'm going to get 4 over 3. Okay. If I take 256 divided by 81 and then divide that by 64 over 27, I'm going to get 4 over 3. No matter what, always going to get 4 over 3 as a common ratio. Okay. Now, the other type of really popular sequence that we have is called an arithmetic sequence. And so with arithmetic sequences, instead of having common ratios, we have common differences. Okay. And so with common differences, there's just a common difference in between each number. So for instance, if let's say I listed odd numbers here, because that is technically a sequence, the common difference in between each number is 2, because the difference in between 1 and 3 is 2. Well, 3 and 1 is 2. Difference in between 7 and 5 is 2. Okay. And so, of course, if we kept on listing numbers that follows this pattern, then of course the next number in this sequence would be a 9, and then the one after that would be 11, so on and so forth. Okay. So it is a recursive sequence because, again, we start off by having a predefined number. So the first number in the sequence is identified. And then, of course, all the other numbers in the sequence are whatever the previous number was plus that common difference. Okay. And here we also see that if we kind of knew what a sequence was, like the list of the numbers was, and we were able to express it algebraically, if we wanted to find the nth term in some sequence, in this particular arithmetic sequence, and we knew what the initial number was and the common difference, we could actually find it just by using this formula here. Okay. All right, so let's go ahead and move forward. All right, so as an example of arithmetic sequence, you see that we have the sequence here. And notice that the difference in between all of these numbers that we see here is 4. So this would be our common difference, 4. And of course, you can see how, according to, I'll scroll back up here, the common difference is just going to be the difference in between, let's call a sub n plus 1 the current number minus the previous number, just a sub n. Okay. And so you see in all those instances, current number minus previous number, current number minus previous number is just 4. And that is what that common difference is. And of course, if we wanted to find out, let's say, the nth term of this particular sequence, we could just use this formula here. So you see that I've actually done that to come up with the first 4 numbers in the sequence. If I wanted to find the 100th number in that sequence, I could do the same thing. I'll just take the first number plus my n is 100 minus 1, and then times 4. And of course, this would be 99. I have 3 plus 99 times 4. Okay. And of course, this would end up just being 399 once we're done. So that is how we could find any specific number in an arithmetic sequence. All right, so let's go ahead and move forward here. So the Fibonacci sequence is another popular one, and it is recursive because the first two numbers are both just 1, and really the Fibonacci sequence is after we define those first two numbers, we just add those first two numbers together. So if we add 1 and 1, we get 2. Okay. Next, if we add 2 and 1, we get 3. Next, if we add 2 and 3, we get 5, so on and so forth. Okay. So we see that particular sequence is just put together by saying, hey, our first two numbers is going to be 1, and then we're just going to add the two previous numbers to get the current number. Okay. Now, the factorial is something that most of you have probably seen before, but you probably did not realize that it is also a recursive sequence. Okay, but by definition, it is. So here, when most people deal with factorials, of course, we know that factorial is just going to be whatever number n is. You just multiply that times all the natural numbers previous to it till you get to 1. So for instance, if you want to figure out what 4 factorial is, it'll just be 4 times 3 times 2 times 1. Okay. Now, the thing is that with factorials, one of the things that has to be understood when you deal with them is that 0 factorial is equal to 1, and 1 factorial is also equal to 1. So these two things have to be previously defined before you get started here. Okay. And so in this instance, of course, if we use the definition of factorial as being a sequence, the whole concept of having 0 here doesn't make a lot of sense, but we could rewrite this factorial so that we end up getting a 0 here if we needed to. Okay, I'm just telling you just from a practical application of using this that we also understand that 0 factorial is also 1. Okay. In general, though, if we were to define this as or write it as a recursive sequence, we'll start off by saying that the first number in the sequence is 1, and then the second one will just be, of course, 2 times 1. Third one will be 3 times 2 times 1. And you can see how that kind of morphs into what the factorial is. Okay. So in defining it this way, what it turns out is that they kind of skip this one and they just start with this one. Okay. But again, in some applications of using the factorial, we also define 0 factorial as being 1 for convenience as well. Okay. And so in general here, we see that the list of numbers for factorial, this could be 1, then 2, then 6, then 24, and we just keep going and going. And if we wanted to write it out in terms of n, that is what it would look like for a particular factorial number. And this is what the sequence of numbers looks like in terms of n. Okay. All right, so let's look at general sequences now. So these are the sequences where we are able to express what the list of numbers is going to look like with just a function in terms of n, where n is going to be a subset of the natural numbers. One of the most popular general sequences that we have is an alternating sequence. And so this sequence, the purpose of it is to make sure that you have proper signage on your numbers in the sequence. So let's say if your numbers switch off from being positive to negative or negative to positive, then the alternating sequence allows you to be able to characterize that properly. Okay. So this alternating sequence, we're going from a positive number to a negative to a positive to a negative. So in general, since we know if we raise any negative number, let's say to a positive power, so not positive, but an even power like 2, then we know that that's going to be a positive number. If we raise a negative number to an odd power like 3, we know that's going to be an odd number. And so we just kind of play around with it to make sure that if we want to start off positive, then we make sure that we have an even power here to begin with. Okay. If we need to start off negative, we make sure that when we start the sequence off, it's the exponent is some type of odd number. Okay. And so in general, this is how we could express that alternating sequence. Okay. And so here, if we're starting off with n is equal to 1 here, then this is going to be the, positive, negative, one. Okay. If we wanted to start off with the negative 1, then this sequence will look this way. So if we wanted -1, +1, -1, +1, so on and so forth, this is how we could write that. Okay. All right, so the next sequence really doesn't have a name to it, but I mean, it's one that you'll probably see at times. And you can just see here that it was just, 1 divided by 1 times 2, 1 divided by 2 plus 2 times 3, 1 divided by 3 times 4, so on and so forth. And so you see, if we list these out with n equals 1, n equals 2, and n equals 3, and kind of break this out and write it to where in the end, anywhere where we see a 1 in this first one, we replace it with n. Anywhere where we see a 2, once we break it out, we replace it with n. Anywhere where we see a 3, once we break it out, we replace it with n. We see that we get this common pattern here of 1 divided by the product of n and n plus 1. Okay. And so this would be the algebraic form of what this sequence of numbers would look like. Okay. And so realize that this is a function and its domain is going to be n values, and these n values are going to be natural numbers. Okay. And so that is a subset of our domain being listed. All right, so this will conclude this first video. And again, the purpose of this video was to kind of give you an introduction of what it is that we're doing as far as using sequences in calculus, to expose you to some general type sequences. Well, I say general type sequences, but to expose you to sequences that we use often. Of course, general sequences is one type, recursive sequences is another, and we went over several different types of those recursive sequences and a few general ones. So in the part 2 video for this series, I'm going to go over some basic facts about sequences. And again, the purpose of going over these basic facts and establishing some definitions is that we want to study the convergence properties of a sequence. And so when I say convergence, all that really means is that if I keep on listing out these numbers here, if my sequence is going to converge, you're going to see the longer I list out those numbers, as n approaches infinity, the number is going to look like they are going to approach some final number at the end. So for instance, to kind of give you a quick example of what that might look like. Let's say if I had a list of numbers here and I had, let's see, 1 and then 1.9, 1.99, 1.999, 1.9999, and I keep on going. So if this particular sequence kept on following this pattern here, then what you would say is that eventually this particular, if we could get to the end of the sequence, it's probably going to go to 2. Okay, so whatever sequence this would be, we're going to say that it's going to converge upon a number 2. Okay, however, if we have a situation where we just have, let's say, a general sequence like this, just our natural numbers being listed out, for here we see that the more we list numbers, the bigger they get. Okay, and it's not going to converge upon anything, because as n goes to infinity, the number that we're going to list is going to go to infinity. Okay, so for those reasons, we say that a sequence like this one will diverge, whereas one like this will converge. And so in the part 2 video, we're going to look at definitions that allow us to be able to see if a sequence has a property that acts like this one, or if it acts like this one, without us necessarily having to list out all the numbers in the sequence to be able to see that. Okay. All right. I'll see you in that part 2 video.